Henrik, we look very much forward. Henrik is from Equinor, obviously. We look very much forward to hearing about where you are in terms of SMR and CCS. Are you there, Henrik?
Hello, can you hear me?
Very well indeed. Thank you, Henrik. The floor is yours.
Good. Thank you. My name is Henrik Andersen. I'm from Equinor. I'm the Vice President in Low Carbon Solution heading. I'm more or less responsible for the technology solution we are using in our different hydrogen and CCS projects. So I'm going to talk briefly about reforming natural gas with CCS. I myself have a 25-year background in hydrogen and CCS. Been in all the heights and the waves. Hope we will do it this time when we talk about hydrogen and CCS. I was in fact in the early 2000s in Norsk Hydro developing the first green hydrogen-based filling station that was opened in Iceland in 2003. So now I'm back in hydrogen again, where we are thinking a bit bigger scale in Equinor with really large-scale projects. So just moving on, because I will not spend so much time on different, let's say, comparisons and so on, but I just flag out two reports where you can find a lot of detailed information and about technologies and cost comparison. It's the H21 North of England report we did 1.5 years ago, and the LMA Energy studies we did and was published in April this year. That contains a lot of, I think, key information and a lot of what I will try to cover in the next, I think, 10 minutes in my presentation. So it'll be quite quick and crisp. But as you probably know, around 75% of all current hydrogen produced today is from natural gas, and it's a really proven and mature technology, and that's why Equinor is really focusing on that, because if we want to meet the net zero ambitions, if we want to implement hydrogen at scale, large volumes, this seems as the most realistic options in the next at least 10, 15, maybe 20-year time frame. Knowing, of course, ultimately that we will get to green hydrogen at the point of time, and I will show you that a bit later in a case study we did. So we're basically talking about two technologies for reforming natural gas into a syngas containing mainly hydrogen and CO and CO2. And that is the steam methane reformer and orthothermal reformer. So steam methane reforming is the one to the left. That's a big box with a lot of fire burners, so you introduce a lot of heat. And inside that box you have some long tubes filled with catalyst. So when they're exposed to heat, they start to convert the methane and water into a mixture of hydrogen and CO2. And we operate these plants around 40 to 50 bar, and that makes it, let's say, a more compact and more cost efficient to remove the CO2, particularly from the syngas stream. So the steam methane reforming is an endothermic reaction. I think that's important to know. It requires heat and we need to supply that in some form. Without any CO2 capture, we use just natural gas. But if you want to do CO2 capture, you can either use the hydrogen you produce or capture CO2 afterwards. That means it's a bit more challenging to meet a capture rate above 90%, which we believe is necessary to really have what we call a net zero. So I think I lost my connection. So thermal reforming is also a very established technology industry. It was also developed simultaneously with SMR around or deployed in the 40s. ATR is quite similar to what we know from coal gasification. So you introduce air or oxygen to drive the reaction. It's an exothermic reaction. That means it generates energy, and a lot of the energy is to be used for producing steam and maybe for further converting methane into more hydrogen. I think the main, let's say, differences between the two technologies when we talk about deployment is that the ATR can be delivered at much higher single line capacities. So we're talking about single line trains or units around the 1.5 to 2 gigawatt. And that's not just a number that we aspire to. That's in fact already done today. If you look at big gas to liquid plants in the Middle East, there we have ATR where produce equivalent to 2 gigawatt of hydrogen. And they've been operating for 15 years. SMR is a bit difficult to scale up, so they have a max capacity. This is correct some wrong figures here. around 400, 500 megawatts. The advantage of ATR compared to SMR is that you get all the CO2 on the syngas stream at high pressure, and that means it's much cheaper and easier to capture CO2. So when you talk about blue hydrogen and achieving high efficiency at high capture rates, we see at least ATR as a more optimal solution compared to SMR. So with ATR, you can probably meet capture rates about 95%, maybe up to even 97%. That somehow becomes like very important when we are approaching the net zero targets. Efficiency is also a bit better, but as you can see on the SMR, if we do not have capture, SMR becomes much more efficient. So you have about 85%. I think that's the main reason that we see that SMR is much more used in the hydrogen industry, because currently it's not necessary or not needed to capture CO2, and then you go for the most efficient one, and then SMR becomes more efficient. But when you adapt CCS and we have to capture CO2, that reduces much more compared to an ATR. So that's just to give you a brief, let's say, comparison of the two key technologies in reforming natural gas. Next is, Europe is really a world leader in that space. It's really the legacy from the early 1900s, where the chemical industry developed in Germany, France, and UK. And you see a famous guy on the right hand side, that's Fritz Haber. He's also known from the Haber-Bosch process of producing ammonia. But in fact, he also patented some of the first SMR concepts in the world when he worked at IG Farben. BASF took the first patent on the nickel catalyst, that is like the key catalyst in reforming hydrogen. And the first SMR was in operation in UK in Billingham in 1936. When I say Europe is world leading, so if you look at supplier space, there's about 8 key suppliers of SMR and ATR. And 7 of these 8 are from Europe. So it's Air Liquide from France, Johnson Matthey from Europe, KBR is US based. You have Linde, Technip from France, ThyssenKrupp, Halder Topsoe from Denmark, and then Arnic Foster Wheeler or Wood Today from UK. So you have really a competitive edge when it comes to reforming natural gas. And it's quite interesting to see. It's not an area where you say the Asian or the Chinese have taken any space. And then I think that should be somehow maybe recognized a bit more, that you in fact have that key position already in reforming natural gas to hydrogen. A key component is of course CCS. Equinor have run, I would say, still the only CCS project in Europe. The first one was Sleipner more than almost 25 years ago. And then Snøhvit 12 years ago. We're now working on a new project called the Northern Lights, starting with some industrial CO2 sources from the east coast of Norway. But the project is developed as an open source CO2 TNS. And we work a lot with the European industry to link up to that store. And really, that's been a really key enabler for European industry that can't either do hydrogen or electrification. They only have CO2 capture as the only option to decarbonize their industry. What's not shown here is that we're also involved in the UK. So we are involved in a project called Net Zero Teesside, where we work with OCI partners, BP, Eni, Shell, and Total to develop a CCS project, and that also comprises a CO2 store called Endurance, which is a huge aquifer containing up to 400 million tons of CO2. People are talking about the potential of CCS or CO2 storage in the North Sea. At least the work that we are seeing done in Norway, UK, somehow shows that it's potential to store maybe up to 100 to 150 gigaton of CO2 in that area, which really is showing that it's really a key tool to plays a key part in potential meeting net zero for Europe, using both hydrogen, blue hydrogen, and CCS. A small case study I said we did is because there's a lot of discussion when we introduced blue hydrogen, is that what about gas logging, what about upstream emissions? So if you take a classical blue concept with an ATR CO2 cap, you need some power to run the air separation to oxygen. We have around 75% efficiency, and that needs to compensate with more natural gas. So to deliver, let's say, 75 terawatt hydrogen, you need 100 terawatt of natural gas. And that means like countries that then we increase our gas dependency. So Equinor has looked quite a lot on how can we reduce that gas dependence and how can we still make our concept not stranded concept. So what we see is that the first step in this aspect is to electrify more of the concept. We can electrify the fire heater, we can do more advanced reforming. So we see we are now using more electricity, which will of course ultimately be a huge portion of renewable, backed up with hydrogen-based flexible power. So we reduce the natural gas consumption by 20%. The next part is adding in biogas. A lot of countries in Europe, Germany, UK, France, etc. have a lot of biogas available. And ATRs and SMR can use biogas same as natural gas as a feed source. So we look at, and that you can find it in these element energy studies that looked into adding in 20% biogas, and by that we are again reducing our natural gas consumption with even more, so 20% more. And then we can look into electrolysis, using electrolyzers also as an oxygen source to the ATR, getting more green electricity into the concept and reducing natural gas. And then we can move on, and the final step is more electrolysis and more bio, and at the end you will not have any, let's say, natural gas, but you still have the original investment in both ATR and CO2 capture, water gas shift and so on. It's not a stranded asset. I think that's really a key message, that we can transform the blue hydrogen concept into green, and will not end up with a lot of stranded assets and wasted investments. So I think this case study illustrates that. The final slide just showing our portfolio of projects. You're probably familiar with that. So we have the Northern Lights, which is a CCS project, and then we have a broad portfolio of hydrogen projects, both in Norway, UK, Germany, and Holland, and we are talking a lot of in partners. And I would say there's a lot of discussion about green, blue, pyrolysis, and cost comparison, that and that. I think that's very interesting. But I think from Equinor, we are a bit beyond that. I think our key focus is how do we develop the hydrogen market? How do we work with power producers to convert their natural gas-based power station to hydrogen? How do we work with industry to convert their boilers and heaters to hydrogen, and so on? So I think that should be a much higher focus, instead of having this almost competition between different ways of producing hydrogen. I think there's no need for this type of competition if we don't have a market. So we need to create the market first. All technologies will play a role, so let's create the market. I think that's my final statement. Thank you.
Thank you very much indeed, Henrik. It was terrific stuff. Because of time constraints, I think we're going to have to move to the final speaker, and then perhaps see if we have time for questions for everybody at the end. Chris, Engineering Manager from BP, we look forward very much to hearing where you are on this point in time. Chris, the floor is yours.
Fantastic. All right, thanks for that. So Chris Gibson, Engineering Manager in BP, sitting at a central team, and we support CCUS and hydrogen activities. So we look at technologies, we support business or early business opportunities. Similar point to Henrik, actually. You know, my team of chemical engineers, we look at both all sorts of colours of hydrogen, whether it's blue, green, or wherever it's produced. So again, I think it's important to think about hydrogen as an important energy source and energy vector, and as a feedstock. And where you apply it will depend on the kind of the timing, what scale you're looking for, what the economics are, and particular locations will have their own preference and their own optimization. So if we kind of move on to, so what are we talking about when we talk about gas reforming? The title actually originally was saying steam methane reforming. I just want to call this gas reforming because there are many technologies out there that you can use for gas reformation. It could be partial oxidation, it could be ATRs, it could be SMRs, it could be advanced ATRs, you can do combined reformers. There's many types of reformers out there, and you have to optimize it to your particular application. But this is kind of just a typical block flow diagram of blue hydrogen, where we're taking natural gas, injecting steam and oxygen into an autothermal reactor. We produce syngas, shift it through many different combinations of shifts, single, double, multiple cases. We then produce a high concentration of hydrogen CO2. We remove the CO2, and that's taken away for carbon use and storage. You can further purify the hydrogen through pressure swing absorption at very high purity rates. Store it in salt caverns to help you with solutions with interseasonal energy storage issues. And then with hydrogen, it has a broad application in multiple different energy sectors. We could use it in transportation, in particular heavy transportation and marine, we think are very viable industries for hydrogen. It can be used in power generation, space heating, process heat, feedstocks. Of course, is the obvious example, which is currently used in refineries. But you can also produce blue ammonia as well, because we've taken CO2 out of the system. We can combine it back with nitrogen, and we can use ammonia. And ammonia could be used, as we know, for fertilizer, but it could also be used as a fuel in the marine industry, for example. There's a lot of industry, a lot of interest now in looking at ammonia for fuel. So why blue hydrogen now? Well, I worked on a project 15 years ago in the UK at Peterhead, and we came up with a similar flow sheet to this. In fact, when we went through FEED and we got planning permission, so we got a long way with this technology. So 15 years ago, we were very confident that we could put all these building blocks together, which are commercially available at scale today. So we could get process guarantees from licensors, we could get contracts with EPC contractors and suppliers to build these plants. So we're confident you can deliver these at scale, and we know these building blocks are already being delivered in the industry. So in terms of TRL levels, we're right at the top of these at this level because we know we can buy these off the shelf today. So why do we need it? I'll just briefly touch on a couple of key studies that are probably well known to most of you. IPCC and also the IEA studies, where they've looked at different scenarios going forward, and both CCUS and fuel switching fit both of these projections. And so what does blue hydrogen bring us? Well, it brings together both fuel switching and CCUS. So it's an industry that can be readily put into practice. We know we can do this at scale. And I'd just like to kind of finish on some examples where you could apply blue hydrogen, because blue hydrogen is going to play an integral role in creating what we call clean energy parks or clean energy systems, also known as industrial clusters in the UK. There's one being developed at the moment in Teesside, which is an OGCI concept that BP's leading on. So that one's moving forward, and in fact they've got post-combustion capture as their anchor project. But if you look at kind of where hydrogen could play, you can see here that hydrogen, blue hydrogen, is integrated across many different clean energy systems in these clean energy parks. So the hydrogen itself, and that could come from green or blue or a combination of, provide heat for homes and industries, fuel for power and transportation, feedstocks to other chemicals. So it's a great way of kind of interacting and encouraging new industries. We firmly believe blue hydrogen can be readily done at scale today, but the infrastructure associated with blue hydrogen can also help facilitate the future for green hydrogen. And CCS can also facilitate other low-carbon solutions such as post-combustion. So if you've got blue hydrogen infrastructure in place, it means you've got also CCUS in place, and that can encourage post-combustion technologies as well. So you can look across many industries to see what the optimal solution is, with an anchor being blue or post-combustion to get these industrial clusters moving. So we see hydrogen as a complement to electrification. We see blue hydrogen as an essential long-term pathway for decarbonising natural gas. It's the most likely economic source of clean hydrogen at scale in the short term, but we see both scope for green and hydrogen going forward. And whatever type of hydrogen, it's going to be specific to whatever region, whatever is available in the region. And that could be cheap renewables, it could be CO2 storage, it could be availability of land or policy. And the infrastructure from blue hydrogen is great for facilitating other solutions. So we see that certainly leading into green hydrogen. So I'd like to kind of leave you with that thought that there's not one particular solution that's going to fit all cases. We need all these examples, but what we can do today is blue hydrogen, and it will help facilitate other industries and other clean-up solutions.